Hello there, welcome back. This is lesson 2 in our acid-base unit. For this video, you should be following along to the note sheet for Unit 10, Lesson 2, Intro to Acids and Bases. So, if you're watching this on schedule, again, make sure you're following the calendar, because the day I record this is not the day that you were watching this. The Arrhenius theory cast learning should be due tonight by 11:59 p.m. Again, make sure you're following that calendar because it does have all the dates that you need to know. Okay, so what are the difference between acids and bases? Let's go into that. Acids can be strong or weak electrolytes in aqueous solutions. Again, when we talked about electrolytes, think back to a while ago. They're things that conduct electricity. And because of that, it conducts electricity because it has, when it breaks up in water, it has those ions, and those free-floating ions allow for electricity to flow. Acids, like HCl, react with certain metals to produce hydrogen gas. We might spend a little bit of time on that, but there is a table in the reference table that we will go back to in our next unit. Acids cause color changes in acid-base indicators. We have a whole lesson designated just to indicators, and so this is just kind of an intro of everything. But specifically, acids turn blue litmus paper red, and if you use a indicator called phenolphthalein, that's what this word is right here, phenolphthalein, it's colorless in an acid. Like we learned yesterday, acids can have a sour taste, and table K on the reference table has a list of the acids that you'll be responsible for knowing. Bases, on the other hand, they can also be strong or weak electrolytes, meaning they also can conduct electricity. But if we're using acid-base indicators, they turn things different colors. They turn red litmus paper blue. They turn phenolphthalein pink. Again, that's not something you need to memorize. We'll work through that later on. Bases are slippery and are bitter. So a lot of them are like cleaning fluids, baking soda, stuff like that. But table L on the reference table has the formulas and names for the bases that you'll be working with this unit. Okay, so when we're talking about acids and bases, for the majority of the unit, we're going to be talking about Arrhenius acids and bases. But a long time ago, there were these two dudes that studied acids and bases, and they had different theories. And we're going to talk about both those theories today, and they're both right. They just look at things from different perspectives. But again, most of the things we'll be working with later on are Arrhenius acids and bases. So this dude named Arrhenius, he is talking about these acids, and he says, okay, cool, if you're an acid, you have to give off an H+, or a hydrogen ion, when you're in solution. So if we have the HCl example, HBr, H2SO4, when you put that in water, those H+'s pop off. And then, because all these solutions are in water, that extra H+ that pops off the acid attaches itself to one of the floating water molecules to form H3O+. So whenever you're talking about acids, H3O+, H+ are essentially synonymous. So Arrhenius said, yo, acids give off H+ ions. So Arrhenius also talked about bases, and he said that bases have OH groups and give these OH- groups away, and those are hydroxide ions. So NaOH, KOH, CaOH2. All of those are key points in bases. So Arrhenius said, you know, if you're a base, you give off this OH-. If you're an acid, you give off this H+. Okay, so question. Which substance can be classified as an Arrhenius acid? Again, that's something that gives off H+, and that is antitress A. Moving forward, which substance can be classified as an Arrhenius base? Remember, bases give off OH-, and the only one with an OH minus is B. Now again, you can also look back at tables K and L on your reference table, because those are good examples of acids and bases as well. Okay, another checkpoint question before we move on. According to the Arrhenius theory, a substance that is classified as an acid will always yield, we're talking about acids, and that's H+. So up to this point, we've only talked about H+ and OH-. So B and D make no sense. OH- is talking about bases. Okay, so let's move forward. So now there's this other dude. This other dude, Bronsted-Lowry, he's studying acids and bases as well, but he has a slightly different perspective on what they do. So he said that an acid is an H+ donor. So if something is donating something, that means you're giving it away. So that's what Arrhenius says too. So they agree on acids. So another thing you'll see as we move forward, H+ is a proton. Okay, so if you think about it, a hydrogen atom, so here's hydrogen, it has a mass of 1 and its atomic number is 1. So again, remember this bottom number, that's atomic number, means it has 1 proton. Its mass is the number of protons and neutrons, but if it's only 1, it means it's still 1 proton. And then an H+ atom is neutral, so it has 1 electron. So a hydrogen atom is only made of 1 proton and 1 electron. But if you have an ion, that means this electron went away, and so now it's positive. So 1 proton is the same thing as an H+. Okay, going back to this, Bronsted-Lowry said a base is an H+ acceptor. So acids are giving away their H's, and then bases have the capability of picking that H up and accepting it. So if we look at this example here, and the AQ got moved. Thank you, formatting. If we look at the HCl, and we look at Cl-, if we go from one to the other, we can see that those two are paired together, but the H on HCl went away, because now there's only Cl-. If we look at H2O and H3O+, those two go together, but it looks like something had to happen to this water to get H3O+. So the H that was on the acid attached itself to the water to make you get H3O+. And we're going to talk about how this works in a lot more detail today and tomorrow and the next day. Okay. So, in this case, let me put all this stuff up. NH3 accepts an H+, and H2O donates an H+. So again, you want to find the things that look like each other and figure out what happened like that. But in this case, NH3 is acting as a base. Again, if you're confused now, it's okay. We will spend a lot more time on this. So a good way to kind of help remember this is that Bronsted-Lowry acids and bases are bad. So BAAD, it stands for bases accept, acids donate. So if you're like, oh my god, I forget which does which, just think bad. Bases accept H+, acids donate. And so we're going to practice with this statement for a while. Now, I'm not sure if you picked up on this, but in the two examples we went with, water acted as an acid in one case and a base in another case. So water can donate protons and it can also accept protons. So if you have, get an actual pen, if you have H2O, if you lose a H, you become OH-. If you gain one and you accept it, you become H3O+. So all these things branch off of water, and so that means water can be amphoteric, meaning it can act as either an acid or a base. Okay, checkpoint question. According to the Bronsted-Lowry theory, a chloride ion acts as a base when it combines with. Now here we're talking about this theory. And that's when you should be thinking about B, A, D, base, accept, acids, donate. And in this case, we're saying chlorine is going to act as a base. It means bases need to accept. And what are they accepting? They're accepting H+. So it's saying that Cl- can be a base if it does what thing? If it has the capability of accepting that H+, that's what makes it a base. Again, we're going to practice with this, so it's okay if you're a little bit confused. The next one says, according to the Bronsted-Lowry theory, an acid is, we're talking about proton donors, acceptors, so that's, you should be thinking bad. So bases accept, acids donate, and what are they donating? That H+. So the only one that makes sense is choice A proton donor only. Okay. Moving forward is something called conjugate acids and bases. So let me just put everything up here and then we'll talk about it. So a conjugate base, first, if you think about any foreign language that you're taking, I know specifically this works with like Spanish and French and Italian. I think if you're conjugating verbs, you have the same stem, but the endings change a little bit. But you can tell they're all kind of part of the same family. They all kind of look similar. So when we're talking about conjugate acid base pairs, you want to find things that look like they could be related. Okay? So if we look at our example, we have, get a highlighter, NH3, and on the opposite side of the reaction, something that looks like that is NH4. So obviously they look like they come from similar roots, and they're similar. And then the other one, you have H2O, and you have OH-. Those two look kind of similar. So those are your two pairs. That's how you find your pairs, finding things that look similar. Now, a conjugate base is what remains after the acid gives up the H+. And a conjugate acid is what is formed when a base accepts a proton. So we're just going to throw out these words with you today, but we are going to spend a lot of time on this tomorrow. But if we look at this example, so we have NH3 and NH4. Going from NH3 to NH4, what happened? What did NH3 have to do in order to become NH4? So NH3 has to accept an H+. So once NH3 accepts an H+, boom, you got yourself NH4. Okay? So if we know that NH3 has to accept that H+, that's what makes it a base. Okay? Now, what it looks like after it actually accepts that H+, that's what NH4 is. That's that conjugate acid. Okay? So the acid is what the base looks like after it accepted that H+. Now looking at the other pair, we have H2O and OH-. So think about it. What did H2O have to do in order to become OH-? So it has to lose or donate an H+. And again, what did we say loses or donates to H+? That's an acid. And then once that acid actually loses that H+, its final product after it loses it, that's that conjugate base. So we're going to practice with this over the next few days. So moving forward, a conjugate acid has H+, a conjugate base pair is the acid with one less H. So if we look at this pair right there, the only difference is that the base has one less H. Acid has two H's, the base has one. Looking at this example, HCl and Cl-, this has an H, this lost that H. So the only thing that's different between a conjugate acid and a conjugate base is an H. So let's try this. So let's figure out our pairs first. So NH3, you want to find something that looks like something like it on the other side, and that's NH4. And then H2O looks like that. So finding your pairs is the easier part of this. So now, in order to go, looking at NH3, to go from NH3 to NH4, it has to accept an H+. So if something can accept an H+, remember, bad. If something accepts, that is a base. So NH3 is going to act as your base. So once that base actually accepts that H+, that's the conjugate acid. Okay. Looking at the H2O example highlighted in blue, to go from H2O to OH-, you need to donate or lose an H+. And something that has the capability of donating an H+, that's an acid. So H2O can donate, and once it actually does donate the final product, your OH-, that is your conjugate base. Looking at the other example, you have HCl right here. That's going to pair with Cl-, and then you have H2O, and that pairs with H3O+. So now in this case, to get from HCl to HCl to Cl-, you have to lose or donate H+, and so that makes this your acid, and that the conjugate base. And then in process of elimination, it's the other one. But to go from H2O to H3O+, you have to gain or accept an H+. And so if you have the capability of accepting an H+, that makes you a base. And the final product is a conjugate acid. So that says Ca. So if you've noticed, on one side of the equation you'll have an acid and a base. On the opposite side you'll have the conjugate pair. Okay. So again, we're going to spend more time with this tomorrow and the day after. So it's okay if you still have questions. So let's just try this. Checkpoint question. It says, in this reaction, which pair represents a base and its conjugate acid? So one of the first things you want to look at is pairs. So we know this and this have to pair together because they look the most similar. And this need to pair together. So we can get rid of choice A because that's not even the right pair. We can get rid of B because that's not the right pair. We can get rid of C because that's not the right pair. So D is the only one that actually has the correct pairing. And then if you wanted to look into this in more detail to make sure that you're right, or you like this topic, going from H2PO4 to H3PO4, you have to accept an H+. So if you're going to accept an H+, this makes you a base, and that makes this that conjugate acid. And then to go from H2O to OH-, you have to donate an H+. So that makes H2O your acid and OH- your conjugate base. But if that part confused you, that's okay. As long as you're just looking for the pair that actually looks like a pair. Okay, let's just try another one. According to the Bronsted-Lowry, the two bases are, so this one we need to do a little bit more work. So let's find our pairs first. So we have this pair, and we have this pair. So looking at the HSO4, to get from here to there, you have to lose or donate an H+. So if you're donating an H+, that makes you an acid, and that makes this the conjugate base. And then in the water example, you have to gain or accept an H+. And if you're accepting an H+, that makes you a base, and this your conjugate acid. So when the question asks for your two bases, well, water is acting as a base, and then SO4 2- is acting like a base, and that is choice B. Okay, so let's just kind of wrap this up for today, and tomorrow we'll practice more on the conjugate acid-base pairs. So just to kind of review what we've done, we talked about acids and bases, and then the two theories that exist with acids and bases. So the dude Arrhenius, he said, acids give off H+ in water, but bases give off OH- in water. And so this is the theory that we're going to be working with most of the time in this unit. So we'll revisit that in a few lessons. But for the next few days, we're going to focus on this dude, where he's talking about just focusing on what happens to the H+. So Bronsted-Lowry says that acids are H+ donors and can give it to something, and bases have the capability of actually accepting it. And so a good way to remember that is bad. Bases accept, acids donate. Now on that note, that is it for today. Tomorrow we're going to practice more with conjugate pairs, kind of very step-by-step work through of them, and that is it. Have a wonderful day.